Good morning, students. In the previous lecture, we have introduced numericals on combination of capacitor. That is series and parallel combinations of capacitor. Now today we'll continue with the more practice of numericals. So here, this figure has been given that in between X and Y, you have to find equivalent capacitance where capacitance 2 microfarad, 3 microfarad, 5 microfarad and 10 microfarad are connected as shown in the figure. So let me take this point as A and let me take this point as B, this to be at C and this to be D for our convenience. Now here, first of all, we have to identify which capacitors are connected in series and which are in parallel. So let me recapitulate that in series combination, charge remain will be same. For each of the capacitors, same charge will be transferred. But in parallel combination, charge will get divided. So when the capacitors are connected in parallel combination, then the positive plate of all the capacitors are connected together. So see here, this is terminal A. So this is capacitor 1, let it be C1, this be C2, this is C3 and this is C4. So out of these, first of all, let it is at positive. This plate is positive and this plate is negative. So now here this A point is connected to first plate of C1 as well as through this lead wire it is connected to point D, which is connected to second plate of C2, and this here, this is first plate of third capacitor. See, we have to identify the combination. Here you can see here what can be the charge coming through the main source. Although what can be the source connected here, we will not mention it here because we have to understand the combination of capacitors here. So here the charge will get divided around these two parts. So now this is the positive plate of capacitor C1. Now this will also be connected to, this should be the positive plate. Also this should be positive plate. Why we are taking it? Because here the charge is dividing at this point as well as at this point. So when charge division is there, when you are saying that all the charge, whatever be the charge is present on each of the capacitor, but the positive plates of all the capacitors are connected together. So now let me redraw it. This is terminal X, this is point A. As for C1, one plate is connected to A point and C2 another one plate is connected to A point, and for C3 also one plate is connected to A point, and this all is having positive charge. We don't know what is the amount of charge present here. We are not finding here charge. So obviously when this is positive, second plate will be negative, and these all are connected to terminal P. So see here, as we are taking see how these are connected to B. See, you can see from here this C point is connected to B, and see here C is connected to second plate of C1, that will be obviously negatively charged, and this is connected to P point, and here it is connected to negative side, in a second plate of C3 also. So what about C2? This C point is common to C1 and C2. So this second plate, the first plate of C2 will also be connected to negative. So you can say that B is connected to C. It means it is connected to one negative plate of each capacitor. So now it is clear to you that C1, C2 and C3 are connected in parallel combination. And further, B and Y, in between these two, one capacitor C4 is connected. Main point which you have to understand, the arrangement. This is slightly different concept. Here you have to identify that all the positive plates are connected together in parallel combination. Why we are just emphasizing on parallel combination? Because here charge is dividing. Here this junction is not a single point. Here charge division is there. At this point, at every point there is a division of charge. So you cannot take this to be a separate. But from this B point there is no further division, so the charge is remaining to be the same. So what you can say that C1, C2 and C3 are connected in parallel. Now recall the formula. For this parallel combination, what will be the equivalent capacitance? C1 plus C2 plus C3. Value of C1 is 2 microfarad. For C2 is 3 microfarad. For C3 is 5 microfarad. So total is 10 microfarad. Now you can easily judge that this is CP, this is B and this is C4. So in between X and Y, these two are connected in series. So now what will be the equivalent capacitance? It will be 1 by CP plus 1 by C4. CP, it comes out to be 10 microfarad and C4 is given to be 10. So taking LCM, you are getting, taking LCM 1 plus 1, 2, this is 1 by 5. So C equivalent will be 5 microfarad. All the concepts are simple. Main point which you have to target here is, that is how the charge get divided, which capacitors are connected in parallel and which are in series. Now, before going to next numerical, let we understand Wheatstone bridge principle. Although this all concept you will study in next unit, current electricity. What is this Wheatstone bridge principle? How to prove it? Here we will simply take or learn its result for application in numericals on capacitor combination. See, as per this Wheatstone bridge principle, here in between A and C, capacitors C1, C2, C3, C4 and this C5 all are connected to form a bridge. And if the values of capacitors are given in such a way that C1 upon C2 equal to C3 upon C4. If the ratio of C1 and C2 is equal to ratio of C3 and C4, then potential difference, there will be no potential difference between B and D, or you can say they will be both at the same potential. So if there is no potential difference, there will be no charging of the plates of capacitor. So this capacitor will not contribute. So what you have to learn, that if the ratio of these two capacitor is equal, you will simply say that C5 capacitor is ineffective. Why? Because it will not contribute. Why? Because B and D will be at the same potential. So in that particular case, only C1, C2, C3, C4. Only these will contribute. Now here, this will not contribute. Why? Because no potential difference, no charging of the plates of this capacitor. Now see here. From this point A, there is a division. It means charge will be divided. But for C1 and C2, same path. It means they are in series combination. Similarly, C3 and C4, these are also in series combination. So now you will take series combination of these two. So let it be CS, this is CS dash. And CS here will be this is 1 by C1 plus 1 by C2, and 1 by CS dash will be 1 by C3 plus 1 by C4. When the values will be given, you can calculate them easily. Now, see here, in this figure, as now CS and CS dash, now these are connected in parallel. Why? Because positive plate of both are connected at terminal A, or you can say the charge get divided. So you can say here CS and CS dash are in parallel combination. So their equivalent capacitance will be CS plus CS dash. These are not actually the formula, these are the method what we have to apply. From this particular result, what we conclude that here in this figure, as the ratio of capacitors are equal, so C5 will become ineffective. Now coming to the basic method, then here C5 is ineffective. Now the concept become quite simple. So let me do one numerical on by applying the concept of our Wheatstone bridge principle. Now, coming to numerical, let's see how to apply here Wheatstone bridge principle. See here, in the figure between A and B, we have to find equivalent capacitance where C1, C2, C3, C4 and C5 are connected in the manner shown in the figure, and each of the capacitor having capacitance of 10 microfarad. So let's see. Here, how to redraw it. This is terminal A. This point is X. At this point X, which two capacitors are connected? C1 and C4. One plate of C1 and C4. And here it is division of charge. So let me take C1 is connected here and C4 is connected here. This is C1. This is C4. Then here from X, one plate of C1 and C4 are connected. Now here after this C4 is connected to point D. Here B is connected to Y. Let me take this B point connected to Y. Now Y point, it is connected to one plate of C5 and other plate of C2. Y is common in between one plate of C5 and other plate of C2. Again, there is division of charge. So it means you can take here one capacitor. This will be, it is connected to Y, and this is here again one capacitor. I am not labeling it right now. I will just tell you one more point. From Y, one is C5 and another is C2. So either of these two, this is C2 or C5 or C5 or C2. As C here, C2, one plate of C2. This plate is connected to Y. So other plate of C2 is connected to C point, which is common to second plate of C1. Repeating it, this is confusing point. As C2 capacitor, one plate is connected to Y terminal, so other plate is connected to C point, and C is a point which is common in between C1 and C2 as well as C3. So it means where in the figure C is common to C1 and C2. See here. Here, if this is C2, so C1 and C2 are connected at terminal C. So obviously this will be C5. And we have seen in the figure that C is also connected to one plate of C3. C is connected to one plate of C3 also. So now we will draw it. This is C3. As per the connections mentioned in the figure, we are trying to redraw it. Now, coming to point D in the main figure. Here D point, it is common. Where? In between second plate of C3 and one plate of C5. It means here D point is also common for second plate of C4. Three connections, one connection is for C3, one connection for C5 and one connection for C4. Come here in the figure. Here D point should be that it should be connected to C3, C4 and C5. It means all these are connected in the parallel. So let this point be D. Just revising this point for you as see in the main figure, because this diagram, if this figure is clear, then the concept is quite clear. As see here, as this point X, at this point X there is a division of charge. It means these two are connected in parallel. Here two connections are there. So you can see here only two connections. From X, two connections for C1 and C4. Now at point C, in the figure, C1, C3 and C2. C is a point we have to choose in such a way that it should be connected to second plate of C1, first plate of C3 and first plate of C2. So here, this is C is common in C1, C2 and C3. D point. D point is common in between C3, C4 and C5. Obviously, these are all in parallel because there is a distribution of charge. So we have taken D point here. And Y point? Y point is common for, as you can see from the figure, Y point is common in between C5 and C2. Y is common in between C2 and C5. Right? This is the first step we have done. I hope these terminal points are clear to you. Now coming to the next step. Now take the ratio of C1 upon C2. This is 10 upon 10. Why? Because each capacitor in the figure is given to be 10 microfarad. This is also equal to C4 upon C5. This is all one. Ratio of capacitors, no unit. We have not to take the unit here, but we have to check the ratio of like quantities will be unitless. So the ratio is identical. So this C3 will not contribute. When this C3 will not contribute, then these two will be in series. These two will be in series. There is no need to redraw it. Now the concept should be in your mind. So now C1 and C2 will be in series combination. Similarly, C4 and C5 will also be in series combination. So let me take series combination of C1, C2. Let it be C dash 1 by C1 plus 1 by C2. Each value is 10. 1 by 10 plus 1 by 10. 2 by 10. 1 by 5. So C dash is 5 microfarad. Similarly, capacitance of series combination of C4 and C5. 1 by 10, 1 by 10. Same calculation, I am taking it directly. This implies C dash is equal to 5 microfarad because the values are all identical. This is C double dash. Now, in between A and B, now you can see this C dash and this is C double dash. These are in parallel. So directly their parallel combination will be C, and it is C dash plus C double dash. It means 5 microfarad plus 5, that is 10 microfarad. So now you can see how simple this question is. Main concept is how to rearrange the capacitor to apply the concept of Wheatstone-Bridge principle. Now coming to next statement. Here one figure has been drawn. Now in this figure you have to find equivalent capacitance between A and B. See here in this figure, this is an infinite ladder has been given. So many numbers of capacitors are connected in the same pattern. So what we have to do, how to solve this kind of numerical? As suppose we say there is infinity. If we add something in infinity or subtract something in infinity, it will not make any difference. If there is a big ocean, if one bucket water is taken out from it, it will not make any difference, or added to it, it will not make much difference to it. Likewise, so from this ladder, if we take that, let this all, which is repeating, this portion is repeating every time. So if we consider this to be capacitance C, let me take the C is the capacitance, equivalent capacitance of this infinite ladder. Actually, we are taking C is the equivalent capacitance of this infinite ladder. And now here for this particular ladder, we will treat it as C. Let's see how. This is terminal A and terminal B. This 1 microfarad capacitance in between. This is 2 microfarad capacitance. And apart from other capacitance connected, we are taking it to be C. So what we have taken, let C be the equivalent capacitance. Obviously for infinite ladder. The shape like a ladder, that's why we are saying it. Now, see these two capacitors. As we have earlier explained that when we have to check whether the capacitors are connected in series or parallel, we always proceed from the back side. Now here you can see this 2 and C. These two are connected in? Yes, correctly you have guessing. This is series combination. So here for this series combination, let equivalent capacitance is CS. So now 1 by CS, it will be 1 by C plus 1 by 2. So 1 by CS, it will be taking LCM 2 plus C. So this means CS will be 2C upon 2 plus C. This is one step. Now, let me redraw. We have to simplify so that no confusion left further. Now here, the series combination of this is CS. You can draw it here, you can draw it here or here. It will not make difference because here in this figure you can see that there is a division of charge. So division of charge means here this will be in parallel to these two. So here this is a parallel combination. Now you will again see that the infinite ladder has equivalent capacitance C. So what you will take it as C. This is a main point. This C will be 1 plus CS. Because we have taken equivalent capacitance of this complete ladder, of this complete network as C. So this is a main point. I am marking it star. If it is correctly you have written, then you will solve it definitely. Now, C will be 1 plus 2C upon 2 plus C. Just your mathematical part, how strong you are in maths, you can simply solve it. So here, this will come out to be, and this is your C equal to, let me take its LCM first. This will be 2 plus C plus 2C. So if we solve it, this is 2 plus 3C upon 2 plus C. Cross multiply. I'm solving it here. This is C into 2 plus C. This is equal to 2 plus 3C. 2C plus C square equal to 3C plus 2. Rearrange. C square minus C minus 2 equal to 0. This is the equation we are getting. Now, it's a concept of class 10 or 9. You can solve it easily. Just form the pairs. C square minus 2C plus C minus 2 equal to 0. Taking C common, C minus 2 plus C minus 2 equal to 0. Arranging in brackets, C plus 1 into C minus 2 equal to 0. Then, here this product will be 0 only when if C plus 1 is 0 or C minus 2 is 0. So from here C is minus 1 or C is plus 2. So out of this 2 microfarad, this will be correct and this will be wrong. Why? Because capacitance is a value, nothing to do with negative or positive value. So as it comes out to be negative, it cannot be negative. Just value cannot be negative, so it is not possible. So value of equivalent capacitance is 2 microfarad. So basically the main point which you have to understand in this numerical, that for equivalent capacitance of this complete infinite network is C, and that C, this will be used here as well as here when you are taking the parallel combination. See each and every step. Now it is very clear to you. Now one more numerical we are doing today. A network of 4 10 microfarad capacitor each is connected to a 500 volt supply as shown in the figure. Here figure has been given. Now determine equivalent capacitance of the network and find charge on each capacitor. See here one network is given C1, C2, C3, C4, each having same value of 10 microfarad. These are all are connected as shown in the figure, and to a potential difference applied is 500 volt. You have to do two tasks here. Find the equivalent capacitance of all these 4 capacitors as well as charge on each capacitor. So now see, as per figure C1, C2, C3, what this is appearing? These are the terminals. Let me label it as A, B. At this point, further division of charge here. Now it means this will be in parallel combination to these. Now this capacitor C1, C2 and C3. Here the same charge will flow because there is no distribution. Further there is no other path. So whatever charge is here on C1, same will be on C2 and same will be on C3. So let Q be the charge on each of capacitors C1, C2, C3. So it will be positive, this will be negative, this will be positive, negative, positive, negative. We have an idea that when the capacitors are connected in series, then negative of one plate of first capacitor is connected to positive of first plate of second capacitor, and so on. So here as these 3 are connected in series, so CS will be the equivalent capacitance. So what is this CS? This will be 1 by C1 plus 1 by C2 plus 1 by C3. And each value is given to be identical, that is 10 microfarad. So when you will solve it, this can be 10 by 3 microfarad. You can solve it by yourself also because this is simple numerical. So this is your 3 by 10. This is not here. In the next step you will get it to be 10 by 3 microfarad. So now here there is one capacitor connected in between, and here it is CS. This is C4. Now CS and C4, these two are connected in parallel, so their equivalent will be CS plus C4. So it will be 10 by 3 plus 10. So take its LCM, 10 plus 30, it is 40 by 3 microfarad. Either you can just keep it as such, or you can simplify it, 13.3 microfarad. This is the equivalent capacitance. So one point that was asked in the statement, determine equivalent capacitance of the network. So now what is the next step? You have to find charge on each capacitor. Coming to the main figure, see here all these are connected in series. So recall the main rules. In series combination, which factor remains same? Charge. So which factor get divided? Yes, potential difference. It means this 500 volt potential, let it be capital V, it will be divided among these 3. V1 across C1, V2 across C2 and V3 across C3. And potential across this C4 will be 500 volt. Whereas for the combination of these 3, this will be divided. If these capacitors are identical, then obviously charge, you can say the potential will also be same. But if capacitors were different, if it will be different, then the value of potential difference will be different. So here you can take V, total potential will be divided as V1 plus V2 plus V3 among the three capacitors which are connected in series. And now put the values as total potential is given to be 500 volt. Now V1, potential drop across C1, as what is the formula of Q equal to CV, general formula of charge with capacitance. Charge on each of C1, C2 and C3 is Q. Q is there and capacitance is also given. So Q upon C1 plus Q upon C2 plus Q upon C3. Now you can also take it as Q 1 by C1 plus 1 by C2 plus 1 by C3, which is from the very first step, this is 1 by CS. This is simple calculation. The method you like, you can do it. Substitute the value of CS here. This is 10 upon 3. So it is 3Q by 10. Now here this capacitance is in microfarad. So when you are putting the value of capacitance here, you should also multiply it by 10 raised to the power minus 6. Why? Because 1 microfarad is equal to 10 raised to the power minus 6 farad. So now just solve it, rearrange it. You have to calculate the value of Q. So here 500 into 10 into 10 raised to the power minus 6 divide by 3 equal to Q. So it is 5 by 3 into 10 raised to the power 3 into 10 raised to the power minus 6. Arrange it. 5 by 3, 10 raised to the power minus 3. So this is 1.67 10 raised to the power minus 3 coulomb. What is this value? This is charge on each of the three capacitors C1, C2, C3, because these are connected in series and for series combination charge is same. Now charge on capacitor C4. Again let charge on this capacitor, it is different. So this have Q, so it will be not Q, it will be Q dash or something, you can denote by any other symbol. So Q dash, when you have to obtain, this will be C4 into V. C4 is 10 and potential is 10 into 10 raised to the power minus 6. First of all, we are completely writing the value of capacitance C4, then voltage 500. So it is 5 into 10 raised to the power minus 3. This is coulomb. So see, in this way you have calculated the charge on each capacitor as well as you have solved the combinations of capacitor to find their equivalent capacitance. So this is all we have done today. We have done few numericals, practice more numericals on the concepts we have covered. It will give you confidence because here this conceptual, this numerical part is very, very important. So practice it. In the next lecture, one more lecture I will take on capacitance numerical in different form. So before that, just prepare all such kind of numericals. Thank you. Have a nice day.